Lecture 29 covers unit hydrograph derivation, basically from real data. And so, we've got this definition of unit hydrograph says that it's 1 inch of excess precipitation following in a certain duration. So we know that it's a hydrograph. The volume is equal to 1 inch or 1 centimeter. And we have some duration that 1 inch or 1 centimeter of rainfall fell in. So if this is a hanging bar graph, which is my hydrograph, it has one increment of rain, and it has some time duration, T sub D, we'll just call it that here, that is the time that it took to get that 1 inch or 1 centimeter of rainfall on. So what we're going to do is we're going to look at using actual real data to derive a unit hydrograph. And we've got two ways of doing that. One is for uniform storms, where the storm is nice and uniform in its rainfall, and it has one single peak, and it's a nice hydrograph that looks nice and uniform. There's no double peaks and no messiness to it. The other method is using the convolution equation and deconvoluting the complex storm. So again, reminding you the unit hydrograph is 1 inch of excess precipitation spread uniformly over a space in the watershed. That rainfall of 1 inch occurs uniformly in time, and there is a given duration for that time. That is called the effective duration. Now, if we look at this derived unit hydrograph, what we have is we have an actual hydrograph that we then have to separate off the base flow. Because again, base flow is not from the runoff process, but it's from the groundwater flow. The excess precipitation is causing the direct runoff hydrograph, the DRH. You've heard me refer to it as that. So we have to separate off the base flow from the total flow of the hydrograph in order to get our direct runoff hydrograph. And so if we look at this, and I've got some base flow here identified, we subtract that off of the total hydrograph, we end up getting in yellow here. You can see we've got the direct runoff hydrograph, which is from the surface response, the surface runoff response. A derived unit hydrograph in method 1 from simple storms, if you can find an individual simple storm occurring uniformly in time throughout a period of rainfall excess and uniformly over the entire watershed, then we can determine the direct runoff by subtracting out base flow. And then we look at the amount of excess rainfall from the volume of that direct runoff hydrograph. And then we would divide through by that amount of rainfall, excess rainfall, by each ordinate of the hydrograph in order to get the unit hydrograph. Method 2 is this deconvolution method that we've talked about, or I mentioned it earlier. That's for those complex storms. So let's look at method 1. A rule of thumb is the storm should be fairly uniform in nature, and the excess precipitation should be equally as uniform throughout the basin. This may require the additional conditions throughout the basin to be spatially similar. Second, the storm should be relatively constant in time, meaning that there should be no breaks or periods of no precipitation. Finally, the storm should produce at least 1 inch of excess precipitation. So here's a great example. This is a much bigger watershed than we would normally do, but it provides some good data here for the example we're talking about. It's 450 square miles. That's a little bit large to derive a unit hydrograph, but it's a good example. Again, it's large because what are the assumptions of unit hydrograph is that the rainfall is uniform in its spatial distribution. When you get these larger hydrographs, or I'm sorry, larger watersheds, it's fairly hard to meet that assumption. You'll notice here that I've got my runoff or my total hydrograph here, and this is the rainfall hydrograph. Now, the first thing you're going to have to do is separate out the base flow. We've talked about that in other lectures about how to identify the base flow, but you're going to have to separate out that base flow because we're interested in that amount of the hydrograph, or that part of the hydrograph that's due to the direct runoff. And again, you can see here in the plot, one way to do that is to plot the hydrograph in log units, log base 10 or log base E versus time. And you can see we've got an inflection point here as the hydrograph, you're coming down the falling limb. And we might call that the point where the overland flow processes give way to the groundwater dominated flow in terms of what's making up, what's constituting the hydrograph. So if we use that inflection point, we can put that here and call all this our base flow. And so this part is the direct runoff hydrograph. Now, if we separate out that base flow, you subtract each ordinate from the total hydrograph from the base flow hydrograph, we can see here I got my direct runoff hydrograph, and I'll just trace that right here. You can see it come down right there. So at this point, I take that direct runoff hydrograph and I determine the volume. And we've covered that. You take the volume, you can sum up the ordinates of the direct runoff hydrograph. So you sum up the QIs and then you multiply by that delta T. That would give you the total volume in cubic feet underneath that hydrograph. At that point, you're going to take and divide that by the drainage area, and that will give you the amount of rainfall that unit hydrograph represents. So if you look at this, we've got this example, and we can get the rainfall that we've got there. And I'm missing, this is in my way here from to move it up. 1.65 inches is the R sub D, that caused the amount of the direct, or that was the amount of the direct runoff hydrograph. If you remember, by our linear systems approach, we can, on a unit hydrograph, we can multiply that excess precipitation by the whatever you have in a particular time duration. You can multiply the excess precipitation times the unit hydrograph to get a hydrograph that gives you what it would be for that amount of rainfall. Conversely, we can divide by the amount of rainfall that occurred and get it, turn it into a unit hydrograph. So if you noted, we had 1.65 inches. If I take every ordinate on my hydrograph, my direct runoff hydrograph, and divide that by 1.65 inches, that now becomes a unit hydrograph. I should put an equal sign there. So if we do that, I take this direct runoff hydrograph, all the ordinates, divide by 1.65, and I get my unit hydrograph. Now that is a unit hydrograph, but there's something missing. I don't know what the time for the effective duration of this unit hydrograph is. So that's where I'm going to do a little more work to try to figure that out. So to do that, I'm going to have to determine a phi index. That phi index is going to be used to figure out the amount of rainfall that's actually the excess precipitation. If I take that R sub D equal to the 1.65, I can do that exercise where I can determine the phi index. Remember, that's back from several lectures ago where I went through and determined a phi index, and I end up getting a phi index equal to 0.2 inches per hour. Now, again, this is from lecture 27, as I remind you. I go through trial and error on my data, and I end up getting this value here of 0.2 inches per hour, just going through and plugging in various values of R. You start with the largest value of the rainfall, get a phi, and then the largest 2 and the largest 3, etc. And what I do is I've got 0.2. Now I take that against my actual rainfall, and you notice here, I've got these are kind of clustered together. And what I typically do in order to determine what this, again, we're after the effective duration, I would be tempted, or what I will do in this was, I'm going to throw away these pieces because there is error in determining these phi index, the phi index. there is some error involved in that. It's not going to be exactly 0.2. We're dealing with real data. And so I'm going to call this an effective duration equal to 6 hours because I've got 1, 2, 3, 4, 5, 6 hours that are clustered together that give me the actual rainfall that's above the phi index value right here of 0.2 inches. And so if I look at this, that's what this, I got a little bit ahead of myself, but that's what that next slide indicates. I'm going to use that as my 6 hours of excess precipitation. I'm getting rid of those small amounts. And so then I've got my final unit hydrograph. That's effective duration, T sub D, of 6 hours. All right, so that covers the first method. Let's move into the second method, which is where you have more complex storms. And there we have to deconvolute the hydrograph and use something called a Gaussian elimination. It's a fancy word for starting with the lowest combinations of unknowns and working your way to where you solve all the unknowns. And so I have to be able to explode this convolution equation. We talked about that in lecture 28, how to go through and get Q1, Q2, Q3, where the ordinates of the non-zero ordinates of the full hydrograph. You've got the non-zero ordinates of the unit hydrograph and the excess precipitation values there. And so what I'm going to do is I take my deconvolution set of equations. Here's what I would have for Q1 is P1U1, and Q2 is P2U1 plus P1U2, so on and so forth. If you recall, I've got capital N as the total number of non-zero hydrograph ordinates. That's going to be equal to what? That's going to be equal to the capital M, which is the non-zero values of rainfall, excess rainfall, plus C sub U, which is my unit hydrograph, minus 1. And so then I can rearrange and calculate what my C sub U is, N minus M plus 1. That would be the number of non-zero unit hydrograph terms I'm looking for. Again, we know all these values of Q1 through Q capital N because that's my direct runoff hydrograph that I have from my real data. I also know my excess precipitation values, P1, P2, P3, et cetera, because I have real data. And we've done this exercise, or we will do an exercise where you have to look at what is the excess precipitation, determining that. So you have to know what that excess rainfall hydrograph, as I said, you use some methodology, phi index. If you had some other excess way to estimate the infiltration and abstraction, you could use the Horton method. You can use green amped. There's other things, and then you have to separate off the base flow from the full hydrograph to get the direct runoff hydrograph. So let's do a quick example here, and let's assume that we already have done that. We know that the excess rainfall here, this is not total rainfall, but excess. So this is going to be my P1, P2, P3. And then this is what? This is going to be Q1, Q2, Q3, Q4, Q5, on down to Qn, which is Q11, right? And so we've got 11 non-zero values for my runoff hydrograph, my direct runoff hydrograph. So remember that N is equal to Cu plus P minus 1. So Cu is equal to capital N minus P plus 1. So that's what, 11. We have 3 values for precipitation. So 3 there. Actually, that's not P, that's capital M. Sorry about that. Capital M is equal to 3 plus 1, which says that what we've got 9. We should have 9 non-zero ordinates of the excess, of the unit hydrograph. So as we go through, we've got M is equal to 3, N is equal to 11. Here I've solved for that 9, C sub U is equal to the 9. And then I just basically start expanding my convolution equation and go through it and solve for the unknowns. And so the first thing I do is I've got my Q1, Q2, Q3, go on through the equations, and I look for my simplest equation that I have only one unknown. Well, I know Q1 and I know P1, right? So Q1 is equal to 428 P1 is 1.06. Again, that's from back here. Here's my P1. Here's my Q1, 428. P1's 106. And I go through and I solve for U1, and that's equal to 404 CFS per inch. And that gives me the first value of my unit height graph. Then I go to my next equation. Well, I know I've got P2, I've got P1, I've got Q2. There's no longer two unknowns because now I have U1 from the previous equation. So all I do is solve for U2, and that gives me 1,079. I keep proceeding through, keep walking this through. I got Q3. I've got only one unknown here, which is going to be U3. Everything else is known. I keep walking through, and you do this for all the equations. I mean, the hardest thing here is to solve for, to explode your convolution equation where you have all the equations at the ready. And so this, you go on through here and look at these, you can see U4, U5, U6, U7, U8, and U9.